Welcome. My paper is entitled Priming for Tonal Harmony, Effects of Temporal Order, and it's part of a special session on the complexity of musical structure. So today I'm going to present the findings from a computational and then a behavioral study that were both designed to examine whether order matters for tonal harmony. So let's start by defining what I mean by tonal harmony. It's a kind of really well-known term in music theory. So tonal refers to music typically that's organized around a central pitch class or tonic. And then harmony refers to the principles that regulate the progression of chords. So tonal music need not be multi-voiced or polyphonic. It need not have chords or triads or seventh chords. But typically when we talk about tonal harmony, we mean music that's multi-voice, that has multiple voices that can carry simultaneous pitches that sound like chords that progress over time, and that those chords progressing over time are constrained by a referential pitch class or tonic. Often we think about harmony in reference to scales, like the major scale, which is this, or the minor scale, and so on. There are many scale systems where triadic harmony might also still be operative. I'll focus on tonal harmony, which tends to refer to the major and the minor scales, somewhat contentiously. So how do we talk about tonal harmony in music theory? Well, we talk about it in reference to a scale. So you can see the musical materials here that I've shown here, this example, which basically just shows, okay, we have a scale, and given a scale, how do we build the chords that we might then use? And you could do that essentially by using the scale to sort of guide your chords. And often tonal music tends to have particular kinds of chords called triads or third space chords that sound like this, and so on all the way up. All of these notes that are stacked above a given scale degree are still part of that scale. That is, none of them are from a different scale system or from outside that scale. We sometimes call these diatonic, so this might be called diatonic harmony. Now, it actually is the case, this is the kind of vocabulary of chords we might find within a given scale or reflected or suggested by a scale, but that's not to say that that's the order in which we might expect chords to proceed. So we wouldn't expect the first chord to go to the second chord and then the third chord and so on. This would be a really sort of base scale theory of harmony. But in fact, we often refer to what's sometimes called functional harmony to refer to the fact that some chords precede or follow others in prescribed orders. And you can see at the bottom here, this is a well-known directed network in an undergraduate textbook that music theorists, music theory students in North America often see by Koska and Payne. So it kind of suggests here are the sorts of chords that would follow other chords or precede other chords and so on. So the question that has concerned a lot of experimental psychologists over the past 40 or so years is, to what degree does knowledge of this scale or of the system of chords and how they proceed and follow one another, to what degree do listeners internalize that information and use it to predict what might happen next given a new experience with music? Well, one way to test this, there's many experimental paradigms that have been used, but one way is to borrow the priming paradigm from corpus linguistics or linguistics writ large for tonal music. So a bevy of studies over the last 40 years have clearly demonstrated that participants are primed to expect tonally related target chords. That is, a target chord that is tonally related to the preceding context from the same scale. This means that if they're primed, they're actually faster and more accurate when responding to some other task that they're given. So, you know, tell me if the chord is out of tune, or tell me if the chord changed timbre, you know, from a harp to a piano. They're faster at that task if the chord was related from the same scale as or key as the prime or preceding context material. Here's a well-known example of this kind of tonal priming effect from Bigot Pinot. We've seen this for melodies, we've seen it for harmonic progressions, it's well known. The question though that's concerned me is, what about if we change the order of chords? In other words, is it the case that it's not just that listeners are remembering a kind of scale system and saying these chords are from that scale, these chords are not, but that they might also think to themselves, well, some chords precede or follow others. That functional harmony is also somehow part of their knowledge store for deciding what might happen next in a given passage of music. Well, there's one priming study that I'm aware of from 2001 by Barbara Tillman and Emmanuel Bigot that looked at this effect. So what they did was a 2-by-2 paradigm where there's a tonal relatedness and a tonal unrelated target given a preceding context, but then they scrambled the preceding context in the other factor, the other experimental manipulation. So you can see here the four scrambled, not scrambled, tonally related, tonally unrelated conditions. And what they found was that scrambling the order of chords had very little effect. Musicians were not faster, or sorry, participants, I should say, were not faster for the unscrambled versus the scrambled chords. So this suggests maybe listeners don't store that kind of information. So this study, the computational study, the behavioral study, were designed to kind of look back at that evidence and either replicate their data or suggest contrary findings. So here are the three research questions that I'll touch on today. The first is, does tonal triadic harmony exhibit order effects? This is already well known to the music theory community, and there's been quite a bit of empirical work to justify it, but I'll do a little myself again here. So that'll be a computational study. Then the next two questions are based on this behavioral study. Does the order of chords in a tonal progression facilitate the speed and accuracy of processing? Are participants primed to expect a target given the sequence of chords and not just the scale that they came from? And finally, the third question, does implicit exposure to or explicit in training in Western tonal music interact with order? Are there training effects for these sorts of data? Okay, so first the computational study. So basically what I did was to look at what are now a burgeoning area of study of a bunch of corpora that have chord annotations. So I took a few corpora that have chord annotations that reflect, broadly speaking, triadic harmony where they're sort of thirds bass chords like these. And then I wanted to look at whether there are asymmetries in the data, whether some chords precede others more often than the other way around. And the same sorts of asymmetries we expect to see in other structured communication systems like natural language. So I looked at these three corpora, the McGill Billboard corpus. It's 738 songs from popular music traditions from the Billboard Hot 100 specifically. The Rolling Stone corpus, which is about 200 songs from Rolling Stone magazine's 500 greatest songs of all time. And the ABC data set, which is a bunch of chord annotations for the complete Beethoven string quartets. So the first two corpora are kind of reflective of popular music and what Western listeners might hear from that perspective. And then the third data set reflects what we sometimes call common practice music or very conventional tonal music, major scales, minor scales, and the kinds of chords that are operative in those musical traditions. The problem with these corpora is that they have very different encoding schemes. It's a little like looking at three different natural language corpora that are from three different languages. You know that they all have verbs and nouns and adjectives, and potentially they've been tagged to tell you that, but you don't know, which noun is related to which other noun in the other language. So I had to create a kind of unifying chord typology that would put all these corpora into one unifying typology. I did that. And I won't go into any more details there, but I'm happy to answer questions later. So really the question I'll look at today is the effect of temporal asymmetry. So given a very simple kind of conditional probability equation that says, given the probability that this chord precedes this one, does that happen a lot more often than when we reverse it, when chord 2 precedes chord 1 instead of chord 1 preceding chord 2. If there are lots of asymmetries, we should see the average asymmetry estimate for a given corpus increase. And what we'll do is we'll look at this for all the bigrams, if you like, the two chord progressions that are across an entire corpus. And then we'll just look at those bigrams that are shared across the corpora because they don't share all of their chords. And what you find, so the blue are just all of the bigrams you might find in the Billboard or the Rolling Stone or the ABC data sets. The red are just the chord bigrams that they share across each other. And what we can see is in either case, they're significantly higher than, with having an error bar across the x-axis. That is to say that there's significant asymmetries across all three corpora. This means that listeners, given exposure to a given musical system, rock harmony or common practice harmony, are hearing very specific chord transitions that aren't necessarily being turned around, so to speak. Okay, so how about the behavioral study? Can we find evidence that participants are actually aware of this kind of knowledge implicitly? So we had 60 participants, 30 musicians in at least the second year of their university studies, and 30 non-musicians with less than 1 year of formal training. We also used musical sophistication index and inventory that tried to get at their musical background without necessarily assuming anything about formal training. In other words, some people think they're not very musical, and then you find out they're actually extremely musically skilled, and they just have never taken formal lessons. That's what the Goldsmith is for. So what kind of materials did we use? Well, essentially we took 16 9-chord progressions from a corpus of Bach chorales from Johann Sebastian Bach, so very conventional common practice tonal harmony, and we modified them slightly so they all had very similar criteria. So the 16 9-chord progressions represented what I'm calling the low temporal incoherence condition. In other words, this is kind of strong syntax. This is what you'd find in real music of a given repertoire. Then they had specific characteristics they all had to meet. So they were all non-modulating. You didn't change the tonal context within the key. There were 1 to 2 applied dominants for the music people. They ended with very conventional ending patterns called cadences. Again, all the stimuli that are used in priming studies tend to do this. And here's an example of one of the stimuli that we used for you to listen to. So how do we create a scrambling paradigm that isn't just sort of a raw permutation where we just take chord 3 becomes 2, 4 becomes 5? That was actually what was done in Tillman and Vigan from 2001. We wanted to build a kind of probabilistic model that would essentially try to learn the syntax of common practice tonal harmony. And then given that knowledge, build a version of this stimulus, a scrambled version of the stimulus that was really incoherent given the syntax it had learned. So in other words, I'm just trying to scramble chords 2 through 8. The target chord never changes. Chord 1 also never changes because it's the tonic chord. It's the chord that indicates the tonal context. So how do we do that? Well, first we used a very small corpus we designed called the Bach chorales melody harmony corpus. There are a lot of Bach corpora out there now. It consists of 100 chorales with Roman numeral and melodic scale degree annotations. Then we used the information dynamics of music model, or idiom, designed by Marcus Pierce. We trained it on this corpus so it could kind of learn the syntax of tonal harmony in these 100 songs, and then identify the scrambled versions of our stimuli that produced medium and really high estimates of model uncertainty. That is, if the model did a really bad job of predicting that sequence, that scrambled sequence, that was the sequence we would use in our experiment. So here is an example. I just played you of the low temporal incoherence. That's the top. I'll now play you the high temporal incoherence. This is where the model looked at this particular scrambled version and said, this is the most unpredictable given the corpus that I've just studied on. So have a listen. Okay, so the design, it's a priming study. So participants were asked to indicate as quickly as possible if the target chord was in or out of tune, where the out of tune chords were tuned 40 cents sharp. So we just tune the whole chord a little bit sharp. We don't care about the task. We throw out the out of tune trials for the most part. We're really focusing on the in tune trials for reaction time. So our dependent variables, we're gonna look at some signal detection theory performance measures. So discrimination or D prime, bias, C, that's across all trials, out of tune and in tune. And then the correct response times for the in tune trials, which is sort of common in priming design and analysis. And then our independent variables, we're looking at temporal incoherence, low, medium, and high, and musical training, whether our participants are musicians or non-musicians. And the whole experiment was pre-registered in the Open Science Framework. So here's the out of tune trial, just so you hear what it sounds like to hear a target chord that's out of tune. So you can hear this a little too high. Okay, so what did we find? Well, here are the model estimates. So this is just the model telling us what we already know from building our stimuli. So the low incoherence condition is the easiest to predict. Cross entropy is essentially average information content or average surprisal. So how surprising was the whole sequence on average? And it's in bits for the people with some information theory background. So the low incoherence condition is telling you it's not very surprising because it's straight out of Bach. Then we have medium, that's somewhat surprising. And then finally the high uncertainty where the model had a really difficult time trying to predict what might happen next. So what did our data look like? Well, here are the correct response times for musicians. We essentially get the same ascending staircase. Musicians were about 100 milliseconds slower on average for the high incoherent condition versus the low, which is a relatively large effect for priming. The non-musician data was actually larger. So there was about 200 milliseconds difference between the highly incoherent conditions, the target chord response, compared to the low incoherence condition. There's also clearly a big training effect here. Musicians are just better or faster, if you like, at the task than non-musicians. What about the performance measures? Well, here's D prime. How sensitive were they to the in-tune, out-of-tune task given our manipulations? Musicians basically hit ceiling. There's this kind of obvious ceiling effect. They're very good at a discrimination task. They're trained to do this sort of thing in ear training classes. Non-musicians were still way better than chance. There's a training effect. Non-musicians are not as good, but they're still way better than chance. So they're doing quite well in the task. They're just not as good as the musicians. And again, there's not really any effect of our experimental manipulations here. We've run a follow-up study where we used an adaptive staircase to determine how out of tune it would need to be, a threshold, an out of tune threshold for every participant. In other words, to normalize for this training effect. And what we find is suddenly both the training effect goes away, musicians and non-musicians get equally good or not so good at the task, equally sensitive, but we also get experimental manipulation effects. So we basically see that they actually get worse at the task as it becomes more and more incoherent. Finally, the bias data. This is really interesting. So we didn't get any effects from musicians. They're basically not biased, whether or not the chord sequence is scrambled. The non-musicians, there's a big effect. So if they just heard a Bach chorale, if they heard something that was very reflective of common practice tonal harmony, they were biased to think that the target chord was going to be in tune. They just assumed it would be in tune because the sequence was normative or conventional. And as the sequence became more and more scrambled, that effect, that bias slowly went away. And they started to just not know whether it would be in tune or out of tune and have to just respond based on the target chord. So a very interesting effect. Okay, so we clearly show that there are order effects based on these studies for our participants, both musicians and non-musicians. But there are some follow-up questions that we're looking at now in follow-up studies. So for example, how do melodic and harmonic syntax interact? We're only really looking at chord sequences here. How do tonal context and temporal incoherence interact? We're not really using the normal tonal context manipulation you read in the harmonic priming literature. We're doing that now. And then finally, do tonal, harmonic, and linguistic structure implicate similar brain regions? This has been a big question in music psychology. Lots of great research. So right now we're running follow-up studies with these stimuli using people with aphasia to see if, for example, if they have Broca's aphasia, comprehension deficits in the left hemisphere, do we expect them to still be able to show priming effects for things out of sequence? If they do, it suggests that perhaps they're using other areas of the brain to deal with syntax and other domains than language, for example, in music. So thanks very much for your attention. Feel free to email me if you have any thoughts or questions, and I'll leave this panel question for the end. Thank you.